My name is Johnny Lee. Woo, yeah, woo! The title of this talk came from a shorter talk that I normally give in 20 minutes, but they gave me an hour at this conference. So I actually am going to leverage, at least weigh the presentation a lot toward the thing that's in the parentheticals, the other HCI research that I think is interesting. Because for the most part, I can cover the Wiimote projects pretty shortly, and a lot of you probably have already seen them already. I put my affiliation as Carnegie Mellon University as well as Microsoft Applied Sciences, and that's largely because a lot of the work you're going to see is stuff I did before I came to Microsoft, or work that's external to Microsoft, including some that's also internal. And the Applied Sciences group, I actually really like the name because it's actually the same name that Bruce Wayne uses in Wayne Enterprises to make all the Batman stuff. So unfortunately, my job is to not make superhero technology for this guy. On the other hand, this guy might be more interested in them. So interaction techniques using the Wii remote. The Wii, as probably most of you know, is a video game system that was Nintendo's 5th generation console, released at the end of 2006. And since its release date, it's shipped over 45 million units worldwide. Now, the part that I think is actually most interesting about the console, and probably a lot of people think is interesting, is the controller. And it's mostly advertised for its motion sensing capabilities. But this is a technical rundown of what is actually in the controller. It's a $40 Bluetooth compatible joystick that you can hook up to a computer. It's got a variety of inputs, outputs, and other interesting capabilities. I'm actually going to first walk through these one by one. Now, as I said, the accelerometer is the sensor that's built into the controller that gives you the motion sensing capability. So literally, it measures acceleration. And it has a plus or minus 3G sensitivity, which means 3 times the acceleration due to gravity. And this is a standard part from a company called Analog Devices, and you could actually buy one individually and just start programming with it if you made your own little sensor device. The part that I think is most interesting about the controller is the infrared camera that's built into the front of it. And it's manufactured by a company called Pixart Imaging. And what's interesting about it is that it actually has built-in computer vision and hardware. So this is a camera that doesn't give you an image, but it gives you coordinates of bright dots. So it automatically does all the image processing, the blob tracking, as well as the centroid calculation to just tell you coordinate pairs of up to 4 dots. Now, the actual specifications of this camera are actually confidential, but the open source community and the hobby community have reverse engineered a large parameter of it, and using the publicly available information on websites like Weebrew and Weeli.org, it gives you 4-point tracking in hardware at 1024 by 768 resolution at 100 hertz. Now, if you are familiar with webcams at all, this is a pretty substantial performance. Webcams are typically 640 by 480 and maybe 30 hertz if you have a good webcam. So this gives you really fast, really high precision tracking at very low cost. When Nintendo sells you a Wii, they also sell you a sensor bar, and the sensor bar actually doesn't have any sensors in it. All it is actually 2 groups of infrared lights. And the camera can see these 2 bright lights, and those 2 dots give the game system information about the orientation of the camera. So I can do mostly orientation information. I can do yaw, tilt, and roll. And I get a little bit of distance by looking at the separation of the 2 dots. From a tactile standpoint, it's got 12 buttons. 11 of them are easily accessible over software. It's a nice ambidextrous design, so people, both left-handed and right-handed, can easily use it. And it has a trigger finger, the B button, and a thumb finger. And in terms of output, it actually has 3 kinds of output. It has tactile vibrational output. This can also be controlled via software. It has an auditory stream, which is about approximate quality of a telephone, and the audio is actually streamed over the wireless Bluetooth connection. It's not playing back files that are loaded locally on the controller. And it actually has a little bit of visual output, so it has 4 LEDs which you can control. The other nice features is that it is a standard Bluetooth device. So if you hook it up to a PC or get it to connect, it'll show up as a normal HID Bluetooth joystick. HID is just a standard interface device class. A mouse is an HID device. A keyboard is an HID device. It has an expansion port on the bottom, which has a proprietary 6-pin connector. It gives you power and also some communication with any external devices. And if you know a little bit of electronics, it's actually very easy to talk to this device, to talk to this port. It has a little bit of onboard memory, and that's where you get to store things like personal profiles, the Mii characters that are on the Wii platform, and it runs off of 20 to 30 hours of operation on just 2 AA batteries. And that's a pretty nice performance for a handheld device with so many sensors in it. Now, if you want to develop your own custom applications, like I said, it just shows up as a Bluetooth device. There are libraries for basically every single platform and almost every single language that you can possibly imagine. And this is mostly thanks to the work of the open source community. The library that I used was written by Brian Peake in C#. I don't know if Brian is in the audience. If not, okay, I guess not. I was told that he would be here. C# I picked up recently, and I think it's a really great language, and this actually makes it very easy to talk to custom hardware devices. So a little bit about the interaction techniques that at least Nintendo wants you to well, at least Nintendo has built into a lot of the games. So the first thing you can do with the controller is simply do pointing like you do in the video games. Now, these are 4 classes of pointing tasks. They all have different levels of resolution, speed performance, as well as feedback control. There's sort of gross selection and navigation, where you're just hitting big targets. There's aiming a weapon or tool, where you need tight visual feedback between the aiming cursor and the position of the controller. There's drawing, where you have to follow an existing trace. And there's push, pull, and rotate tasks, which are all done with a camera. Those are not done with the accelerometer in most games. The motion-based input is often directional shaking, which is essentially button replacement. A large amount of acceleration simply triggers an action. There's analog shaking, where you integrate the motion over time. So basically, you get a measure of how much energy the person's putting into the controller, and that gives you some way of making your character run faster or making the pump push faster. You can also do tilt control. We are in a constant 1g acceleration field due to gravity. So if you were in space, an accelerometer would actually show zero acceleration in all directions. But if I'm just standing here, there's actually a 1g acceleration going down, and that's how you can do basic orientation detection with the Wii. It's also what people use on the iPhone accelerometer as well to get orientation of the screen. And then there's more sophisticated swing simulation, where they try to track the dynamics of a large movement. Doing that, however, is a relatively complex algorithmic. It requires a lot of math, essentially, to get that right, and is actually not quite reliable in all cases. If you actually look at the amount of data that's coming from one of these controllers, it's fairly impressive. When you combine this with the nunchuck attachment, you get the joystick. The nunchuck includes a joystick, 2 buttons, and as well as another accelerometer, 3-axis accelerometer. So if you look at the amount of data coming from this controller, the Wii gives you 13 digital inputs and 12 analog inputs. That's quite a bit more bandwidth than actually even the sophisticated-looking Microsoft 360 controller. And just in comparison, the scroll mouse is only 3 digital, 3 analog inputs. So there's quite a rich amount of information you can get about input with these 2 in your hand. Now, interesting projects by the developer community. The first one I saw, and the one that I really like, is in the upper left, where they attached a broadsword to an industrial mechanical assembly arm, and when they swing the controller, the robot arm tries to mimic their motions and swing the sword as well. The one to the right of it immediately is I think it's a 16 servo little micro robots. You can buy these for about $1,000, and to actually make it do a motion, you typically have to specify the angle for every 16 joints. But instead, what you can do is map the motions of pre-programmed motions to simply physical motions done by the controller, and you can make the little robot mimic you as you dance or you punch. The one in the upper right, when you have motion input, one of the first things that people want to do is simply map it to things that we already do physically. And playing music is a very physical activity. So if you look on YouTube, you look on the web, there's a lot of great projects of people turning the Wii remote into a musical instrument or controlling some sort of synthesizer. I gave a talk at Brazil a few months ago, and the session that followed me was a whole Wiimote band. There was like 4 people all playing with Wiimotes, and it was kind of an interesting experience. Because the camera allows you 2D pointing, a lot of people started off with doing 2D pointing control on the screen. And then once you have 2D pointing control on the PC, you want to do things like play your Flash games and use all the development tools that you're familiar with. Now, the projects that I did 3 projects using the camera, and they've altogether gotten over 11 million views on YouTube. Just out of curiosity, how many of you have seen one of these videos? Okay, that's about half of you. So it just tells me a gauge about how quickly I should skim over this. Since only about half of you seen it, I'll probably spend a little bit more time on it than I normally would. So the first project I did was finger tracking and object tracking. Now, if you're familiar with motion capture in the movie industry, the way they do that is that they have a rig of cameras around an actor, and the actor wears little reflective tags, and the cameras can see the light that's bouncing off the tags. The camera that's in the Wii remote is also a camera, is also specialized to look for bright dots and give you their position. So what you can do is put a little bit of reflective markers on your fingers and put an illuminator around the camera, and you can track your fingers in thin air using the Wiimote. So here's a video of that working. So here, I'm just tracking my fingers in thin air. There's a Wiimote on top of the TV. There's an infrared light. I can get far away from the TV, and I can track the location of one finger. I can generate click events by simply bending my finger. It makes the tape disappear. If I put a piece of tape on each of my fingers, I can now track 2 points. So I get this sort of science fiction Minority Report-like interface that everybody really, really wants, but no one's really used for a long time, for the price of a Wiimote and a couple of infrared LEDs. And then here I can sort of do the hello world of multi-touch, which is a 2D grid manipulation or photo manipulation. So there's definitely lots of limitations to using the Wiimote to do this. First of all, you only can track 4 points. We have 10 fingers. So you can't do everything that you want, or you have to really think about the limitations of your design if you decide to use the camera for your application. But you could get around this by using multiple Wii remotes, or somehow using active markers instead of just reflective tape, and somehow blinking them in the right sequence so you can actually pick up more than 4 dots. There's no inactive cursor feedback, which means you don't know where your finger is if you're not actually clicking. This is actually a relatively big problem. There's 2 solutions to this. One is you can simply respond to mouse up events where it disappears at the location, or you track your thumb and forefinger and then you look for pinches. A couple of people, including some people here I've talked to, have actually done that, where they create 2 sets of gloves and there's 2 emitters on each one. You could hover and then click, hover, click, and drag this way. You do get a lot of arm fatigue. Minority Report is very attractive for people to sort of blog about and take pictures of, but as soon as you do this for more than 30 seconds, you get something what's called gorilla arm, and that's because your arms feel really heavy and you start to get cramps in your arm. So in reality, this is good for maybe short bursts of navigation, or in a more horizontal format where you're working with a tabletop or some sort of drafting board where you can take some load off of your arms. With a big IR emitter, you also have problems with unintentional reflections. My glasses, for example, were generating a lot of bright spots so that the camera was essentially track the location of my head for a little bit. Now, the second project I did was making very low-cost interactive whiteboards with the Wiimote. And this uses the same component of the Wiimote, which is the camera, which allows you to track infrared dots. But instead of tracking fingers with reflective tape, I'm simply tracking these little pens on the left, which are about as complex as an LED flashlight. It has a battery, a button, and a light. So when you press the button, the light turns on. When the light turns on, the camera can see it. And when the camera sees it, it can tell the computer where it is. And you can use that to control the cursor. So let me just show you a video of that. Okay, so here I have my Wiimote just pointed at a projected display, and I do a standard 4-point calibration like most touchscreens, and this allows me to turn a passive wall into a large interactive whiteboard for about $50. And you can see it's precise enough to definitely be usable with Windows desktop. Now I'm going to skip ahead. The nice thing about using a camera to do this is if I point the projector at a table, I can now turn my conference table into a large multi-touch interactive whiteboard. I said multi-touch, but this part of the video demonstrates that. Now, if you don't happen to have a projector, you can also do this with a tablet PC. I'm simply pointing the Wiimote camera at an LCD display, and now I turn a normal laptop display into a tablet PC. If you're really keen, you're noticing in the video I'm turning a tablet PC into a tablet PC. Okay. So the IR pens are really simple, as I mentioned. I've seen YouTube videos of elementary school kids doing this as a science project. They get their parents to help them, but for the most part, it's about a weekend project for even people who are unfamiliar with electronics completely. I didn't do a very good job of explaining how to build an IR pen in my video, so people actually made YouTube videos also explaining how to build these pens. If you don't want to build your pen, you can buy them off eBay, because other people are making these pens and selling them to other people. I was thinking about manufacturing pens to help me, but they've already sort of done it themselves. Sorry, to help people, because they couldn't build it, but they're already doing it themselves. There's actually even I've gotten emails from people in like South America and Europe and Asia who are setting up small companies or small consulting companies to actually help schools set up Wiimote whiteboards in their classroom. So I'm starting a whole economy around this product. The open source community has taken my little bits of research code and ported them to a much nicer version of Windows. Made a much nicer Windows version. They made a Mac version and a Linux version. Here's a picture of a classroom in the Netherlands that I've never been to, but you can see at the very top of the screen, there's a little Wiimote attached near the projector. This is a YouTube video of an elementary school teacher explaining to other elementary school teachers how to set up a Wiimote whiteboard in their classroom. I really like this one, which is because interactive whiteboards are now so cheap, this teacher can actually create 2 of them in his classroom. And what he did is he split up the class into 2 teams and did like a relay race of just solving math problems. There are limitations of using the Wiimote as a whiteboard replacement. It definitely does not work as well as one of the commercial products. It has a maximum resolution of 1024 by 768, so it's not going to be able to handle fine writing, and it's certainly not going to replace your Wacom Cintiqs or anything like that. But it's definitely good enough for basic gross manipulation and pointing, which is what a lot of classrooms need, and perhaps even presentation needs. Things you can do to solve some of the other problems is simply, another thing is that the camera-based approach is very sensitive to occlusion. If you walk in front of the screen, you also walk in front of the camera, and that means you actually can't interact with the whiteboard if you're in front. You can solve this a little bit by either positioning the camera in a more convenient place so you're less likely to block it. If you are fortunate enough to set up a rear projection setup, you can actually put the camera next to the projector and rear projection, and then the camera has a very nice view of the screen and never gets blocked, and the tracking quality is very good. But you get about 80% of the way there for 1% of the cost of an interactive whiteboard, and I think that's actually valuable to a lot of people. And those kind of solutions do help a large percentage of the population. The third project I did with the camera is tracking your head for desktop VR. So what is desktop VR? Well, if you think about most displays, they're normally used to display a flat image. And what desktop VR does is essentially change the way this image is rendered based on the angle that you view it at. So this is called view-dependent rendering, and it's not a new idea. I definitely didn't invent it. It's from the early days of virtual reality research. And the way this is done with the Wii Remote is that you wear a pair of glasses that have infrared emitters in them, and then you put the Wii Remote next to the TV, and that's a camera looking back at you. And so we can see those 2 dots, and then it can give you the head tracking illusion. So let's see this. Try it again. There we go. So this is what 3D display, what a normal video game might look like. You know, it looks kind of 3D and has all the perspective and visual cues that 3D rendering provides you. But as we move our head and look at the screen at different angles, it doesn't really change. If you turn on view-dependent rendering or head tracking, this is the illusion that it gives you. It provides you with the motion parallax that you would get with real objects. So it looks as if the objects are moving as if they were really there, and this allows you to duck your head and look behind objects. If we move our head closer to the screen, we get closer to the objects, and if we can even put our head behind the frontmost target. So we're really getting into the same working volume as the virtual objects. If you look at the frontmost target, it actually has this illusion that it's floating directly above the laptop screen, which is about 2 feet in front of this, 2 feet in front of the TV. Okay. Oops, I'll kill that. What's kind of neat about this video is that it's a technical educational video, and it became the top-rated YouTube video of all time for about 10 weeks. But then I was usurped by this ventriloquist up on the left. Now, he's really funny, so I didn't feel too bad about losing that #1 spot. Now, you don't actually need a Wii remote to do this. You can do this with a normal webcam. But for the performance reasons I talked about, the Wiimote actually provides you slightly better tracking. You also don't need to wear anything on your head to do this. Face tracking technology, as you see on the left, has actually gotten quite good over the past few years. So with a laptop that has a built-in webcam, you can actually do this type of experience. And I haven't actually seen an implementation of this that I felt like that met the performance bar that I thought was required to actually make this useful, but we're definitely getting there. And as cameras improve, as computation improves, and as the algorithms improve, this is definitely possible. And I actually find this a very compelling scenario for usage because people have their laptops. It doesn't require any additional hardware, and you can pick up your laptop screen and then move it, and then render a virtual object as if it was attached to the display. Though the reason why this works, this illusion works, is because it uses motion parallax. And that's basically the technical term for the observation that objects near you move faster when you move your head than objects further away. And this is a pretty well-known perceptual phenomena. And in 1993, there was actually a spatial study where they had people do a 3D task. They either had motion parallax only, or they had stereo 3D only. And it turns out motion parallax provided a much better sense of understanding of the 3D space. So bang for the buck, motion parallax is going to do a little bit better than stereo. Now, there are limitations of this also. I'm an engineer, and I almost always start off my talks by talking about what's wrong with what I did. At least that made my advisor always very angry. The first one is that the perspective is only correct for one person. Everything on the screen, all the pixels are dedicated to that one viewpoint, so someone else looking at the screen, it's not going to look quite right. But there are ways you can get around this. You could use split screen. You can use shutter glasses. There's also a limited tracking volume. If you have seen any camera-based tracking system, you know that there's a trapezoidal area that's covered by the camera. And if you step out of that volume, it can't see you, and the experience breaks down. So working with that is designing your experience to work around that is important. There are hardware approaches, which is using multiple cameras or wide-angle lenses, but that usually comes at the sacrifice of a tracking resolution, which means the stability of your tracking point goes down. You can't touch the objects, unfortunately. As soon as they sort of 3D, you want the corresponding tactile experience, but that currently isn't quite doable with sort of technology today. And you get conflicting stereo depth cues. Those of you who are really sharp will realize that the YouTube is a mono view. It's only one eye, essentially. And the illusion actually works really well when you only have one eye. If you have two eyes, you get a conflicting stereo depth cue because the two eyes are also expecting slightly different views. Now, this isn't a big problem. The illusion still works pretty well, but there's a conflicting point that reduces the strength of the appearance. Now, again, there's technology you can throw at this too. You can use polarized glasses, shutter glasses. There's actually a variety of ways of doing stereo viewing. There's anaglyph blue and red. There's polarized glasses. You can use active shutter glasses. And to my surprise, a lot of the display technology companies are really interested in pushing stereo as the next step past HD. So active stereo shutter glasses may actually make it to market despite the amount of physical overhead one has to wear these glasses. And then there's something called audio stereoscopic, which is doing 3D without wearing glasses. But I think the correct solution to all these problems is simply to make pirate games and give everyone eye patches. If you remove this for a second eye, the illusion will actually work but a lot better. Now, the fourth project I did with the Wii Remote, a lot of people actually haven't seen, or not nearly as much as the other ones. But this one did leverage the camera as well. I didn't advertise it as a Wiimote project because it was part of my academic thesis work. And in academia, talking about game technology is still sort of an iffy topic. But it's the concept of spatially augmented reality. And this is not my term. It's actually coined by someone named Ramesh Raskar, who's done a lot more work in this space than I have. But it's the basic observation that we perceive the world as light, which is reflected off other objects. And that is our perception. And if we can control the light which hits those objects, we can control our perception of what those objects are made of, or even where they are and what they're doing. So if you have a 3D model of what you're projecting onto, you can actually augment the appearance of that object with textures, with information, with other interactive components. Doing this for static objects sitting still with a projector sitting still can be done with a graduate student calibrating it for about 30 minutes. But to actually do this in reality, in any real-world scenario, requires relatively high precision tracking technology. And the Wiimote camera is not bad, at least for the price. So I'm going to show you a project I did using the camera to do augmented reality, to explore augmented reality experiences. And it's the idea that we think of displays normally as hard, rigid devices, but with projection technology, we can project onto anything. So this is actually a surface that's being projected onto and tracked in real time, and a display is being simulated on a piece of cardboard. And because I can project onto any material, I can actually project onto flexible material and unfold it. So this is a newspaper concept. It's a newspaper, so I can unfold it twice. You have to tape it first, but yeah. This is the scroll, so you simply unroll more screen as you want it. This is an umbrella concept. It's sort of a weird geometry, but if you actually think about it from sort of a display area ratio to storage volume ratio, it's actually quite good. You get almost a square meter display in a very, very small volume that you can open up very quickly and collapse very quickly. This one is my favorite, which is the folding fan, simply because you actually can hold it in one hand, you can interact with it with another hand, and then you can fold it up and put it back in your pocket. Now, because the Wiimote only does 4 points, it does actually put a pretty strong constraint on the complexity of the screen geometry. You can't do, say, a screen shaped like a dog, because that's just not, you don't have enough points to do such a complex object. Most of the demos you saw in that video were all planar in some sort, and now it's simply registering onto the planar form, and the math for doing this is relatively well known. Now, that kind of covers the projects with the Wii Remote, and I think it's a really neat device, and it's actually really easy to work with. There's a lot of tutorials on the web for building your own projects. This part of the talk actually is the part that I find much more interesting, and is probably going to be new to most of you, even if you've already seen my videos. And it's about all the other cool HCI research that either I've done or colleagues of mine have done that I think the world should know about. And I've broken this into three parts. They're mixed reality devices, output devices, and input devices. Now, what do I mean by mixed reality? So if you think about the interface between a computer and a human and a computer, there's this media in which we have to communicate. And for a lot of us, it's a mouse and keyboard. But mixed reality devices is simply joining the physical input and digital output into the same space. So a lot of the tabletop you've seen, I think, I would classify as this, which is fundamentally different from, say, a mouse and keyboard, which is physically and spatially disjoint from the actual input you're putting. This is a relatively well-known project called Reactable from MIT Media Lab, done back in 2003. And just to give some context, especially if you're in the web technology, you're used to the world changing in 18 months. Hardware changes on a much slower time scale, so these sorts of explorations were relatively new and novel at that time. This is a project from Sony Research Labs done back in 1999 by a guy named Jun Rikamoto. And this is actually a really nice demo that I think has some concepts which I really wish we had today, but they don't quite exist yet. Oops. What happened to my VLC player? Let me just... Here we go. So what's on this kind of table is a projector and a camera on the ceiling above the table. And when these people come in and they bring in their laptops, the camera automatically recognizes the location of the laptops on the table, and that gives the system spatial knowledge about the physical relationship between two laptops, people working together. So they move their laptop, the tracking keeps up. They can simply drag something off their desktop onto the table, They can drag something off the table onto their computer. There's a camera above them, so they can take pictures of physical things. They get a digital version of it, and then you can drag that onto your computer. So this is multiple people working together in a collaborative way, and they're designing a PowerPoint slide simply by dragging their assets onto the table into a shared space. This is a project, Microsoft Research. So the rest of the talk is going to be lots of these little snippets of awesome things that don't quite exist yet. This is a project by Andy Wilson. The next 3 or 4 projects are all by Andy Wilson. He's a researcher at Microsoft Research. And this is a system called Play Together. And this is a projector camera system that you can simply place on a table. And it turns the area in front of the table into interactive space. There we go. So here it is. This is a projector, a short throw projector, and a set of cameras and an IR emitter, which turns this space into interactive. So one of the things you can do is that if you have physical objects you place in front of the projector, those get registered by the camera. So this is 2 people playing checkers remotely. So their image from their camera is being projected onto your physical board. All right, so there's no keyboard, no mouse, no computer for that matter. They're simply playing checkers. So this is the same idea with chess. I'm trying to find the part where he actually moves the chessboard. Okay, registration, yeah. So the thing is that you have a disconnect between physical and digital, but with the camera tracking, what he can do is simply move the physical chessboard, and all the digital content stays registered appropriately. So both of them can sort of dynamically move their physical references, and all the experience stays maintained. This is one where they're simply doing a collaborative drawing. So one person draws the base of the house. The remote person sees the house projected on their sheet. The remote person starts adding to that drawing. This is also one by Andy Wilson, and the setup he has here is simply there's a webcam on top of the monitor pointing straight down over his keyboard. And using some relatively basic computer vision work, he can actually track the locations of the hands using just the webcam. That by itself is not enormously interesting. What's most interesting is the fact that he actually also introduced a reliable way to actually detect tracking and pinching. So he here simply puts his hand in the space, he pinches his thumb and forefinger together, and the camera can recognize he's made that shape. And what he can now do is actually turn that pinch into a click and drag objects around on the screen simply by putting his hand and pinching them together. He can do single-handed, he can do multi-handed. This is a close-up of what's actually a little bit more about what the computer vision algorithm is doing. You see the little red oval appear when the system registers he's pinched his fingers together, and this gives you X, Y, 2D positioning. He also gets a rotation information out of it, and if I skip ahead, so here he's just doing a demonstration where he's controlling his cursor. So he can do rotation with a single hand. There's no 2 points. He can do X and Y translation. And he will also do Z zooming simply by moving his hand closer to the camera, and then makes the oval bigger, and that acts as a fourth input axis. Let's see. Yeah, so here he's zooming in simply by bringing his hand up and down. It's not the slide. Where is it? There we go. This is one of the new a research surface prototype, which is actually 4 feet by 6 feet. And the reason is because when you go to this size, you can actually bring in a lot of these collaborative experiences and start talking about putting large physical objects on the table. So this is an experience where people have their own keyboards, people have multiple mice. Let me show you the video of that. So it's affectionately called 4 by 6. And I just want to show you a couple of the experiences. These are borrowing many similar ideas from the Sony video where they're combining physical objects. So you can use a physical whiteboard, you can use the normal tools that you're familiar with, and the digital capture integrates with that. So here, hopefully it'll find it. Here, the system knows about keyboards, so when you place a keyboard on the table, it actually generates GUI around the keyboard in a physically orientation correct way. It may be easier for me to just talk about it than try to find it in the video, and you can just watch it to accompany. Oh, here it is. So he puts the keyboard on the table, it recognizes it there. When he starts typing, a search box appears right above the keyboard, and then brings up all the image searches, and now he can just simply drag the images from the search results onto the table, into the shared space. You can add physical mice to the table to extend your reach because there's a physical limit to the human body, and using other instruments like mice is helpful. Here's an example where he's using a physical whiteboard and there's a camera above the table as before, and it captures what he just drew and turns it into a digital form. And then he can make a lot of adjustments which are typically what you could normally do in a physical space that would be hard to do in a digital space. This is a really, really nice work by a guy named Hiroshi Ishii, who's now a Media Lab professor. This was done back in 1992, so almost 15 years ago, or more than that. And this is, again, using displays in space in a more interesting way than we typically do today. This was a remote collaboration tool, and the metaphor that he was trying to simulate was simply 2 people separated by a piece of glass drawing on opposite side of the glass. So I have video of this. Unfortunately, it's a little bit harder to scrub through and find the examples, find the good examples quickly. But the nice thing is about this is that simply by using technology in this way, you preserve all the spatial cues that are natural to human communication. Left is left to you, right is right to you. If I look in the upper right-hand corner, you know what I'm looking at simply because you can see my eyes and the gaze. You can, again, draw in spatially co-located manner, even though you are physically not co-located. He also took a lot of these interaction concepts really far, almost to the point of being artistic, which I think is fantastic, and I find a lot of his work really inspirational. This is work that he did by assuming, what if the interface to a computer was something malleable? What if you were molding clay or molding sand, and that was your interface and that was your input? So what he had is a 3D laser scanner sitting above a table of sand. So when you push the sand around, the computer rescans the 3D form, and they can make the environment react to it. They can make a water erosion simulation. They did a lot of landscaping demos with this, and it's a very, very nice piece of work. This is also in the realm of trying to somehow merge the physical and the digital. One of the problems is that when you move a digital object, any physical counterpart which may be attached to that digital object doesn't move with it. So on the screen, you can move rectangles around simply by changing the variables of its coordinates. But say you put down a piece of whiteboard, or you put down an object which is associated with that, and that doesn't necessarily move with it. So what they did is they did what's called a actuated workbench, which is a large array of electromagnets underneath the table, which could be programmatically controlled. And so these little pucks you put down, the computer could also move interactively as well. And you can do a lot of software-like constraints on physical objects. So one of the applications on the right was like a mobile phone cell tower planning simulator, where what you want to do is get optimal coverage, and you don't want too much overlap in the cell tower coverage. So there's this distance constraint. So when you move this cell tower into this area that already has a lot of cell towers, the other cell towers actually move away from you. And it's all physical, which means it's inherently collaborative and multi-user at the same time. Now, these little Pico projectors I'm sure you've been reading about, these have actually become commodity items a lot faster than anyone in the research and technical community has expected. I mean, we saw these back about 2 or 3 years ago, and we're like, wow, that's really cool. So it's going to be like probably $800 or $1,000 for one of these little Pico projectors. But they came down to $200 and sub $100 speeds a lot faster. And almost too fast for us to find really useful applications for them, other than these mobile phone portable display concepts. Just to give you an idea how long this has been looked at in research, this is what academics used to do well before they were actually a really reasonable size. They'd strap on huge vests and strap on a full-size projector and a full-size camera and walk around the world and see what you can do with it. These are the projector modules in some of the shipping handheld projectors today. You can see that they're quite small. A lot of what's remaining in the weight of the device is power, heat dissipation. And in fact, this starts to become a very engineering-related focus where efficiency becomes key because A, that means your battery can be smaller, and 2, that means it can be physically smaller because it's not quite as hot, and so you can shrink the size of them. So a lot of lighting technology. The progress in these has largely been in advances in LED illumination technology or laser-based illumination technology. When these become available, there are people who've actually thought about the idea of handheld projection for quite a while, and this is some work done at University of Toronto in their HCI lab. What they did is they made the assumption that it's going to happen and we'll have tracking of handheld projectors. So we'll just use a high-end 3D motion capture system and use small handheld projectors and figure out what you can do. And so they have a lot of these really nice concepts where there are multiple people who bring their projectors together. It automatically does display spanning. You can annotate you can leave annotations in physical areas. So if I walk up to this side of the room, or if I walk up to this chair and I leave a note that says Dave's chair, I can walk away, and that annotation is still on that chair, even though I go to another location. When someone else who has a handheld projector can walk around, they can then see the annotation that's physically located. There's a lot of interesting concepts about merging documents. So you have your Word document, I have my Word document, and we simply move our projectors together, and that has a sort of inherent implicit merging. You can do conflict negotiation on scheduling simply by projecting both your calendars. You merge them together. It says, okay, they're overlapping, and then show me the intersection between them. Another interesting thing you can do, at least conceptually, is do head-mounted projection. Now, I'm sure a lot of you have heard of head-mounted displays. This is not pointing the projectors into the eye. It's actually projecting the light out into the world. And this gets back into the spatial augmented reality. And one of the interesting, one of the cute things someone did with it was did an invisibility cloak with these devices. If you put retroreflective tape in the environment, that light that comes from the projector bounces back into your eyes, and so you can project what would be behind that object, and it would appear to be transparent. Unfortunately, you have to be wearing a head-mounted projector for it to look invisible, so it's not exactly a very good cloaking technique. But there are some interesting applications where when people get their own version of a display, and that inherently gives you your own perspective of digital material, and that allows you to do a lot of interesting concepts. I wish I had a little bit more time because there's some neat things in this space, but they're sort of hard to talk about or talk about quickly. One of the nicer uses of this approach of projecting onto physical objects has been in the medical domain. I'm actually surprised at some of their uptake on these technologies. This is what happens when you combine projection with a non-visible light image sensor. So a camera can see infrared, it can see X-rays, it can see ultrasound. So we can't. But we can see visible light, so the system translates those non-visible light images and projects them back onto the patient. And so this essentially gives the doctor non-human visibility or superhuman visibility. This is a project out of IBM research in Boston called Everywhere Displays. And assuming your projectors are cheap enough to actually instrument, place them to the room for general purpose use, and turning any surface into a display, which they did is they simply placed a steerable mirror on the front of a projector. And this essentially programmatically allows you to throw the projected image anywhere in the room. When you have the entire room registered, that means you can say, give me a display over there, give me a display over here, give me a display right, over there, and the computer figures that out. It figures out the registration, and then can turn that passive surface into an interactive one. One of the scenarios they work through was these retail spaces of the future where you walk up to a product shelf and there's currently just cardboard or metal shelving around it, but a system could recognize you're interested in this product, and they simply generate a display next to the product and displays co-located information appropriately. And you don't have to spend the expense of actually putting LCD displays everywhere. I mentioned this earlier, and this is the shader lamps work. Actually, I wish I had video of this one. I don't. The one on the right, I helped a little bit with, which was they had a 3D, they had a gray physical model of a Volkswagen Beetle, and they also had the 3D digital model in the computer. And using this idea of visible or projected augmentation, they can actually give the physical model a custom paint job. They can make it look like it's driving down a little road. So you can imagine showrooms that actually customize the location, the appearance of products simply by changing the light that hits them. This is from my thesis work, which also talks about advanced projection applications, which are now a little bit more practical given the evolution of high-speed projection, such as DLP. So if you're not familiar with DLP, DLP stands for digital light projection. It's owned by Texas Instruments, and the way it works is that it actually has, every pixel is a tiny, tiny little mirror. And these mirrors are flipping back and forth at tens of thousands of times per second. It's pretty amazing that it works, considering a projector can be a megapixel or 2 megapixels. So that means 2 million little mirrors moving at tens of thousands of hertz. What that means, though, in the way they generate grayscale is that there's white, which is always facing you, black, which is always facing away from you, and gray is simply vibrating at some duty cycle, which is closer to always toward you or closer to further away. And that's how they create grayscale. The way they create color is they put a color wheel that cycles between RGB, and if it's your eye actually does the integration to make a single color image. Now, to generate a wide color space, they actually have to get the mirrors to move very, very fast, which means they could actually project black and white images at hundreds of thousands of hertz, or hundreds of thousands of times per second, which is well above what your eye can do. So this is exploring some of the things that you can do when you have high-speed projection. So, there we go. So in the research space, you saw the kind of neat concepts you can do if you have registration of the projector onto these surfaces. You can create augmented reality, you can create track displays, but how do you get that calibration? With the Wii Remote, I was able to do it with the camera, but the problem with the camera is that it requires putting LEDs on the surface. It requires a lot of control with the background. If there were other bright infrared spots in the background, the camera approach wouldn't work. This is how to actually use a projector to locate objects. So using a projector as an input device. What's on this little board is very, very low-cost light sensors. And what these patterns are doing is actually uniquely encoding every single pixel. So when you look at the pattern that's coming from the light, they actually tell you exactly where that sensor is. And you get pixel-perfect registration of where that surface is in the projection area. And let's see. So here I'm just doing the calibration a little bit faster. And then with hardware acceleration, you can turn this little piece of wood into an LCD display, or the appearance of an LCD display by, oh, I didn't show the video. Where'd it go? Anyway, once you have the quad, the corners, you can then render video in a warped manner, and it actually looks like a small portrait display. Let's see. Calibration and tracking it. There we go. This one is QuickTime. Okay. That's okay. The only other application I was going to show you is that this works for multiple projectors too. So if you have a grid of projectors and you simply want to create a single projected image, you simply do a calibration of one display and a calibration of the second one, and that gives you all the information to actually create one seamless image simply by placing two projectors together. So the second component category that I want to talk about is interesting display technologies, or interesting output. As this includes more than just displays, but displays is the most interesting one because we're very visual human beings. So these are some interesting projects that I've seen over the past few years that might be entertaining. and potentially expiring because some of these may actually become useful or realistic products in the future. This one is probably not going to become a product anytime soon, but it's the only real 3D display that exists. And the way it works is that it generates floating balls in midair that you can actually see. Now, the way it actually does this is using the intersection of very high-powered lasers to plasmify the air molecules. So it's actually generating small balls of lightning for every single pixel, which means A, it requires a lot of energy to make these displays. 2, it's very loud. You know, it sounds like you've seen video, like probably at a science museum, you've seen like the generators and the static electricity is going, bzzz, and you can see the guy on the right has safety glasses on. So it's actually not very safe to work around, but it is the only true 3D display that exists, at least holographic 3D in the concept that we think of science fiction movies. The thing that is closer to being useful and is also 3D requires projecting onto some surface which reflects the light into your eye. And the way these work is, again, you sort of heard me talk about the technical description of why high-speed projection is useful. When you have a plate of a projection screen which is spinning at around 3,000 RPM, you don't see the screen anymore. It just looks like a haze. But when you look at light which is reflected off of that, you can actually tell the computer to illuminate every single position in 3D space. So the one on the left is USC, which is a recent one, which actually there's a technical reason why this is a more interesting advancement over the one on the right, but it's probably too difficult to at least appreciate. But these have been around for a few years now, and the one on the right is Perspecta, which is 2006. But because it's a high-speed spinning plate, you don't want to touch it. And it's kind of unsafe to be around, so they put them in these giant glass cases, or you're not allowed to get within 3 feet of the display, which means interacting with them can be a little tough. Now, the holy grail in display technology and display research is what's called a light field display, or a 4D light field display. Now, what a 4D light field display is, if you normally think about normal LCDs, you turn on a red pixel, and the light from that red pixel kind of radiates in every single direction. It looks red regardless of what angle you view it at. What a light field display is, so these concepts are sort of introduced in the head tracking work, but what a light field display is tries to capture all the rays of light that would pass through this surface if it were a piece of glass. So if there was sunlight coming in this direction, it would capture all the sunlight, all the energy, and reproduce it going back in that direction, rather than uniformly in every direction. So for every single pixel, it regenerates the ray that may pass through it at every single angle. And the reason why this is called a 4D light display is because you have two axes of x and y on the screen, and you have 2 dimensions of angle. So altogether, that's 4 dimensions that the display has to generate. Now, that sounds weird in science fiction, but there are actually research prototypes of this. The way they work is very similar to the way stereo displays work, just scaled up quite a bit, or it's like a stereo display on steroids. So the way stereo displays work is you have 2 eyes, and each eye needs to receive an independent image. They essentially get completely different views of the same object. And displays do this by having some sort of grading, so that when you look at the grading at one angle, you see one image. When you look at the grading at another angle, you see another image. And that grading is designed to be about the same interocular distance of the human eyes for a small sweet spot. And so you can create these displays. Now, a separate image for every eye means you need to capture a separate image for each eye, which makes these stereo camera rigs. Now, instead of doing 2 eyes, you do the exact same thing for every pixel on the screen. And you get arrays like this, which is a Stanford project creating I think a 16 by 16 pixel light field. So it's essentially a camera for every single pixel. And with that information, you can tell the computer to say, well, I have all the rays from every single pixel over a 16 by 16 pixel array. Now, give me the rays that intersect at this point. And that essentially allows you to simulate as if you took a picture at this angle, and you then say, well, give me all the rays which intersect at this point. And that allows you to generate a new picture that you never actually took by simply taking the rays of information. This is very heavy to do, very expensive to do, and not very practical yet, but new sensing technologies, new optical technologies are bumping the scale up from 16 by 16 pixels. And I've seen the highest prototype I've seen, I think, was 128 by 128. It's a squaring, so this is an exponentially difficult problem. But manufacturing and certain engineering leaps may actually make this practical. On the display side, so this is the capture side. On the display side, you need the same thing. You need an array of projectors because it has the same optical behaviors as the camera. So what this is a project from Mitsubishi Electric Research Labs where I used to intern at. And what they did is they did a retroreflective screen. They did two versions. One was a retroreflective screen. The other one was a lenticular screen, which is lots of micro lenses. But essentially, they regenerate all the light rays at once on the surface. And when you look at it, it looks 3D. And everyone else around it, it looks 3D. And it looks as if the people are actually really there, just in really low resolution. It's because it's actually regenerating all the light that would come through that surface as if they were physically there. Now, some technologies that might actually help move this forward and becoming much more of a reality. One of these is called wedge projection, which I think is a pretty neat little optical device. And what this does is it's a slab of plastic that is shaped in a very particular way such that if you project into the side, the image comes out the front. And you get a square image. So that means you've collapsed the throw volume of a projector. Where's the projector for that? It's way back there. That entire projection volume can now be collapsed into about 3 inches thick if you put the projector in on the side. It's pretty neat for that reason, but it's also very neat because you can do the same thing with the camera. If you put a camera in the side, you now can move the camera on this direction. And it allows you to do some really crazy optical stuff with folding camera and projection technology. This is one example of using some wedge work in a head-mounted display. So there's a little projector in the side of the glasses, and the rays of light bounce around in the lens until it reaches the appropriate point in which it exits the lens, and then it actually creates a display in front of you for actually very little optical weight. Now, these still have the problem in that they generate a fixed image at a fixed distance. And that is a problem because your eyes focus on objects at different distances. So if I actually want to overlay a virtual material onto this surface versus that wall, those have very different optical properties because of the distances. But if you are able to reproduce the light field through a wedge, you can actually regenerate the light rays that would be coming appropriately at this one and at that position, and you can actually create these science fiction like augmented reality glasses with a realistic experience. It's still probably at least a decade or two out, but all the little seeds of the ability to do it are there. Now the images on the right are from this really nice Japanese animation called Denu Coil, where all these kids grow up in an environment where all the kids have augmented reality glasses, and what sort of social mechanics arise, and what sort of games do they make. So it's actually kind of a neat animation I'd recommend looking at. So e-paper and OLEDs are also really exciting to talk about, or at least it shows up in the media a lot. And we keep thinking that these are going to be the panacea of display technologies because we can fold them up, they're low power. But as you see, no one has actually released a foldable display product. No one has actually even released a bendable display product. And the problem is because you can bend them, but you can only bend them about 100 times before they break. Or you can only bend them with a radius that's pretty big. So if you want a really tight radius so that you can fold it up, or you want to bend it for a lot of times, the manufacturing, the technology just isn't quite there yet. So it's unlikely, and the way the technology is working is that it's unlikely to ever get us to the point where we can think of displays as foldable as we think of the paper as foldable. And the limitation is largely what's called the backplane technology. It's not the light emitting part or the part that generates the display. It's the part that actually actuates those pixels. So it's all the transistor arrays and all the plastic logic that has to go behind it. And this is the part that's fragile. And this is the part that doesn't quite have the performance yet. But it could with some material science. But it's unlikely to ever become truly foldable as paper is without breaking. Alternatively, with the small handheld projectors or the head-mounted projectors, you could use non-light emitting surfaces and actually put the light onto the surface from remotely using a projector. These are just pictures from the video I showed you. So another mode of output is haptics, and haptics haven't really made a lot of noise recently, but I think there's actually some very interesting work going on that might make it into products sometime soon. These were sort of, the one on the left in particular was kind of the state of the art of haptics for a while. It's the Phantom pen. This is what's technically called a grounded reflective force device, which means it is anchored to the table. When you push on it, it pushes back. The more recent technology is shown on the right, which is called butterfly haptics, and that big donut is a giant electromagnet. And you're holding onto the other end of a piece of metal. And when that magnet turns on, it can move that handle around. And it's actually impressive because they can actually regenerate very, very high fidelity experiences. They can make it feel like you're pushing, rubbing a pen. You're never touching this object because you're always holding onto the hand. So you always have the sensation of, oh, I'm touching an object with a probe. But when they do that, they can actually make it feel like, oh, I'm rubbing across a pillow or I'm hitting concrete. And the illusion is actually quite good. Problem is that it's kind of big. They're big and they're kind of expensive. And the movement volume is very small. But there's a lot of nice projects like this one, which is called an ultrasound tactile display. So what it actually does is it regenerates, sort of like the lightning ball display. It simply generates tactile experiences in thin air. And the way it does this is that a grid at the bottom is a set of ultrasound emitters. And if you ever watch the way waves propagate in water, you know they'll create interference patterns. So what this is doing is it's creating interference patterns in ultrasound, and it gets them to all intersect at this one point. And that's the point where you're touching. It doesn't feel like there's something there, but it doesn't feel like there's something physical there, but you can definitely feel the sensation of something in that presence, in that volume. This is a really nice piece of work from Northwestern University, which is using ultrasound vibrating discs. And it's kind of it's really interesting work, mostly because I felt these things, and the experience is extremely compelling. But what this disc does is it vibrates at around 40 kilohertz, so 40,000 times per second. And when you touch it, that amount of vibration actually generates an air cushion beneath your finger and the physical surface. And because it's computer controlled, they actually can control that size of the air cushion. So if they make it smaller, the friction goes up. If they make it higher, the friction goes down. So they can make it ice slippery or feel like a dirty piece of glass. And that's their sort of dynamic range for texture. But with that, they have very high resolution ability to generate tactile experiences. So they can do fish scales, they can do rough spots, they can do hard edges, they can do bumps. The main problem with it is that you're vibrating a surface at 40,000 hertz, 40,000 times per second, so it can't be very big, because it can't. The larger it is, the more energy it takes, and the more likely it is to just shake off the device. There's also another nice project from Sony Research Labs, which was using piezo elements to click a screen. And my understanding is that the BlackBerry almost went with this technology. I can talk a little bit more about why we think they didn't, but the basic concept is actually fantastic. This is the only demo that I've used that actually made me cuss out loud because it was so good. What it does is that it's a piezo element that shakes the entire screen when you press a button. So when you press physically, the software event triggers, and then the piezo element creates a very high frequency click. So it actually feels very much like you're pushing a physical button into the screen. And the sensation is incredibly, incredibly compelling. A project that I did that was essentially inspired by this is called the Haptic Pen, which is the goal was to expand this experience up to larger screens as well as expand it to multiple people. So in these desktop or these wall-sized displays, you can't shake the entire desk or you can't shake the entire wall. But what you can do is put the haptic feedback in the pen itself if people are using pens to interact with the system. Now, we've seen lots of pens and handheld devices with little buzzer motors. But the problem with buzzer motors is that it feels like a buzzer motor. It doesn't actually feel like a real button. So what this does is it actually puts a little solenoid on the back of the pen, and the direction of the forces is actually very important. When you press on a screen, the force vector is through the tip, through the pen. So if you actuate it, use the actuator and actually push applying that same force vector, you can create a very compelling touch experience. A demo that I really wanted to do with this is combine it with a Noto pen tracking, which is the tracking which allows you to know where you are on just a plain piece of paper, or a slightly non-plain piece of paper, but it looks like a piece of paper to you. Is that you can then draw a button and then push it as if it actually physically existed. I never quite got around to that demo, but I thought that would be fun to make. This was a project out of SIGGRAPH, which is a conference on computer graphics, 2007. And it observed that we often experience the world through vibrations of objects through our fingertips. And what they did is they simply put a little band across the front of our finger, which could be mechanically actuated. So when you hold this little empty box of clear plastic, you move it around and it feels like there's a steel ball inside. It's very, very compelling. It actually worked extremely well. They tried to scale this up to a whole hand the next year. The problem is that when you do a whole hand, you're now wearing 5 of these, one on every single finger. And if they want to try to simulate physical objects that are large, you cannot create the physical representation of it to push back. And so they just only had thin air interaction, and they had a tracking system on the hands, but the problem is that it didn't have the reflective force, so I could simply move my hand through this supposedly rigid volume, and it breaks the experience. But if you believe that it was there and you kind of closed your eyes and you felt around it, you could actually feel the whole object pretty clearly. This was a nice piece of work done by some of my colleagues at Carnegie Mellon. It's very simple, but at least to get you thinking about the possibilities, which is dynamic haptics or dynamic tactile displays. What they did is they projected onto a flexible membrane and used air pressure to change the physical sensation of the contours of the display. So they can now make a physically indented button or extended button, or simply make the tactile button disappear completely programmatically. Now, the last part is going to be talking about input technologies. And actually, this gets from like relatively traditional to more weird at the end. So I'll be ending on the weird point. This is a project, again, by Andy Wilson, who was actually at Microsoft Research back in 2002. This is almost a precursor to the Wii Remote. It has a gyro, it has an accelerometer, it also has a magnetometer in it, and it has a package which essentially, a software package that allowed you to hold this wand in a room and could figure out what you were pointing at without a reference system outside of it. And so he had these demos where he could simply point this wand at a lamp and turn the lamp on, and point it at a display and turn the display off. You've probably seen Jeff Hahn's work with FTIR. This is what drives the CNN Magic Wall, I think it's called. He came up with a very nice way of being able to do reliable touching on very large surfaces at a relatively inexpensive cost. But it is a projection camera-based system, so it requires deep displays, displays which are reprojected or a large amount of volume behind them. This is a work by one of my colleagues who's now at Microsoft. He used to be at Mitsubishi Electric Research Labs, and one of the projects they did there was a touch table back, I think, in 2001. And what this does is, the unique thing about this table is that it does not just multi-touch, but it actually is multi-user in the sense that it knows who's touching where. It's not just, all the touches are not the same. So it knows John over sitting on the left is touching the left-hand corner, and knows Mary on the right is touching the other right corner. And it can associate touches with individual people. This is good for implicit social control over objects when you're mitigating passing control of objects in a social experience. It also is very good in terms of accounting who did what, where, and when. 3D input is another range of technology that people are really interested in. It's been explored been explored for a while in research, but none of the technologies or approaches have actually been very good at figuring out a way to find commodity versions of doing 3D input without wearing gloves or motion capture suits. But what's kind of neat and impressive is that the laser scanning technology and the infrared sensing technology that you might have seen that actually allowed the robot cars in the DARPA Grand Challenge are becoming commoditized very soon. The one on the bottom is a camera by 3DV, and it actually gives you a pretty good point cloud at consumer level prices. Now we just have to figure out how to turn these point clouds into something useful. This is a project by a guy named George Klein, and he's a computer vision researcher, and this is the state of the art in computer vision tracking that I think is interesting from an interaction standpoint. We've all seen the visions of the future where you hold up a cell phone and you see augmented images placed over what you're looking at. The problem is that they have an information database problem because you need to know what you're looking at and what the information is displayed, but you also need to know how to figure out you're looking at that object. And this is video that I think has a lot of promise in at least getting us there. For those of you technical in this room, it's called keyframe-based SLAM. SLAM stands for simultaneous location and mapping, which is a robotics term. What he's doing here, he's just have a webcam hooked up to a laptop, and he's in this storage room, and he points the camera out, and it figures out the important edges and important points to track. And so now he's just walking around a room, and he's looking at new objects, and the computer is actually keeping track of where all those objects are. And it recognizes, what's most importantly, it recognizes this object is the same as the object I saw before, and so they're the same object. And so he can literally just walk around the entire room and get a 3D scan of the room, and the computer knows exactly where the camera is in that room. So he gets 3D, a 6-degree freedom input from a standard camera. The processing power to do this is out of the realm of cell phones at the moment, but definitely could be within a couple of years. So here he's just moving quickly. This is showing a robustness test where he's simply just moving around the camera around the room pretty wildly, and the system maintains good tracking and recovery. This is a French company called Sensitive Objects, which takes a completely different approach to doing touch detection. And it's actually a pretty impressive one that I think has a lot of interesting properties. What they're doing is they're actually looking for the sound that you generate when you touch an object. And you've probably seen some of the store displays where you walk up to a window and you tap on it or you bang on it, and then it's like a bang touch display. Those systems use time of flight. So it's watching the time that it takes for the wave to propagate through the surface, through the material, and then it figures out the triangulation of where you touched. The way this company is doing is with pattern matching. So it actually doesn't know anything about the geometry of the screen, and it's looking to say, this sound sounds a lot like the sound when you touched here. And when you build up a large enough database of those, that means you can now make a touch screen. The neat thing about it is that they can do any shape they want. They don't have to do flat screens. They can do a vase. They could turn your car into a touch surface. They can turn arbitrary objects. They did a project with some people where they turned the floor, and they were able to track the footsteps based on the sound propagating through the floor. This is a very nice piece of work from Intel Research, Seattle. What's on the left is actually an RFID reader worn in a bracelet format. It's not an RFID watch, it's a reader. So what they can do is they can place very low-cost tags around your house, say on your mug and your refrigerator or cereal or remote control, and they can recognize when you pick those objects up and when you interact with them. And the application that they're working for is for long-term care of the elderly. So you can sort of monitor what they're doing and you figure out what they're seeing. Whether or not they're active and what they're up to. You can tell whether or not they've picked up their medicine recently. You can tell whether or not they've entered the room or which room they're in based on what light switches they touched recently. So it's a very, very smart way of doing fairly detailed location and activity sensing for very cheap. Another activity sensing project was done by my colleagues at Carnegie Mellon, which is simply listening to the water pipes in your house. And you can actually infer a lot of information about what the person is doing and when, and even who's doing it, because we have different behavior patterns, simply with a few sensors in your basement. This is a nice piece of work also done by some of my colleagues at Carnegie Mellon, which is a very, very low cost. It's technically called a multispectral sensor, but basically it's an RGB LED, an infrared LED, and some light sensors, and they can measure the reflectivity of different devices, of different materials at close proximity. The application is that if this was built in on the back of your cell phone, it would be able to recognize the material of your jeans, the material of your table, the material of your backpack, and it knows where it is. And it can react differently, and it can have different power behaviors. It can notify you differently. And it can even notice that it's on a new surface, so it might be stolen or it might be in some new area. And at Microsoft Research, one of the things I did was looking at brain sensing technology. We were literally trying to figure out if we can read your minds. The answer is not really, but you can get some useful information about the cognitive state of the person with very low-cost equipment. We're starting to see some consumer products which advertise this, but it's the amount of information you get is very poor. What I think is actually more interesting derivative of this work is something called human as a sensor, which is we are very good at dissecting certain types of environmental scenarios. For example, if you're driving, we're very good at measuring, detecting live versus animate versus inanimate objects, which is something computers are very bad at doing. So one thing you can do is you want to sort a large database of animate and inanimate objects. You can put a human in front of the screen, strap some sensors to the human, and the computer can actually read the human and tell whether or not this image is alive or not. The more probably obvious application of this is emergency or piloting scenarios. You're a driver, you see an accident on the road, you have this huge physiological response, and the car doesn't know. But the car, even if you believe in the robot car scenario, we have all these radar systems on the front of the car, and recognizing an accident is very difficult. But the human has a huge response you could easily measure and make the car respond appropriately. Due to time, I see I'm running out. Just quickly, there's a lot of interesting work in being able to measure your muscles directly. So you can interact with objects simply by twitching your fingers, not actually pushing buttons, but actually measuring the muscles inside your body. In terms of muscle sensing, the tongue is a very articulate muscle. Some argue that it's the highest bandwidth output device that we have, simply because it drives our language. Prototype 1 is sticking an optical mouse in our mouth. It's gotten a bit more sophisticated recently. And there's a couple of people at Microsoft Research working with the University of Washington with their nanofabrication lab, which is a lab that actually does electronics on a contact lens. And this has actually a lot of really neat abilities. If we can actually run computation there, if we can put a display there, if we can do other types of sensing. I'm going to skip that one. All right, I see I'm over time. Unfortunately, I was going to give a little bit of a rant about where I thought HCI was going, but I'll just stop there. Unless people ask a question, I can talk about that. Thanks. Thanks.
Hi, my name is Jeff Carpenter, and I only have one eye. So of all these projects, my favorite is the pirate patch.
Great.
I think you should all come to my level.
Yeah.
But second, at TED, Patty Mays gave a great demo of a wearable augmented reality device that you might want to check out. If anyone else hasn't seen that, it's in line with some of those future directions.
Yeah.
Oh, okay, B. So, the question I had quickly was the nice thing about what you did is you use kind of standard bits and pieces that you could buy from a supermarket or kind of build around you, using open source software. A lot of the stuff that I've seen in the past has been kind of, very expensive rigs and really kind of, I'm wondering how much work do you think will kind of move from the labs into kind of more of the open community, and where does that kind of leave the labs?
That's a big struggle with academic research, because they can make lots of assumptions about whether or not this is practical or reality. They don't actually have to kind of attack those problems, and they just have to show feasibility. And that's the goal of academic research, and it's up to people in tech transfer. And the position I'm at Microsoft is actually somewhat a tech transfer position, where I look at the ideas, sift out the ones I think actually can go somewhere, and then try to talk to the right product groups to make sure that they actually can be integrated. But there is a lot of these trade-off and consequences, especially in these large table rigs and augmented reality rigs. They assume that we have 3D tracking systems, or they assume you have a very large floor space and can afford a large tabletop system. But those assumptions actually end up turning into okay assumptions when other technology and other domains actually become good. So, for example, that camera tracking system that I talked about, a lot of the research stuff assumed they put a motion capture system in order to explore the ideas, and they assumed 6-degree of freedom tracking was going to be for free. The computer vision tracking system I showed you actually demonstrates it could actually be for free, because the camera in a cell phone would be smart enough to actually do 6-degree freedom tracking of the input, which now means you can do all those assumptions become valid. So it takes time, and it definitely takes some finesse to figure out where the two plug together, but that is a skill in itself, certainly. Oh, okay, there's so.
You had some face tracking earlier where the computer vision could recognize a face and see what it was looking at. Is that kind of technology high resolution enough to actually tell where you're looking? So not necessarily where your head is facing, but if you're looking, if you had a camera and your laptop, could it tell where on the screen you're looking at?
Yes. Face tracking is pretty good at that. There's also eye tracking technology, which is looking at actual pupil gaze direction. And that first requires registering on the face, finding your eye, and then looking at the ratios of certain reflections in the eye. And then it can actually, the high-end systems require your head to stay still, and then you can actually look at character level resolution. The ones that allow you to move your head for freeform still work. They're just lower resolution. So they probably have 3 centimeter accuracy at a standard viewing distance of a monitor. But there's some research systems in activity analysis which actually does face tracking for gaze detection among a meeting. So they can actually tell who's looking at who when and what happened and how the communication flow occurs as a result.
It wouldn't be quite, it's not quite good enough to track, like let you control your mouse.
Like a mouse replacement or something? Yeah, probably not.
Okay.
At least not to the point where it would be an attractive alternative for someone who is able-bodied.
Got it.
It is actually used a lot in disabled places, but they are willing to put up with a lot of constraints in order to use a system like that.
Okay, thanks.
Yeah.
Hi, I know we're a little short on time, but I'd be interested if you can go on at least a mini rant about where you think HCI is going.
Okay, I'll take the question right behind you first, and then we'll see if people stick around. We can do that. Oh, sorry, you're actually waiting for.
Okay, yeah. Just something popped in my head when you showed that one image talking about different fingertips. Has everyone looked into using as a kind of a data analysis and data input method to say, for example, you would show lots of images you needed to classify to a human, and say you had like 5 selections of plant, animal, mineral, whatever, and they could quickly it's because that's something that we could process very quickly, and they could indicate that by maybe tapping one of their fingers. You know what I mean? So I'm wondering if everyone's looking to like research like that, where you use that kind of human classification and turn it into a very simple cognitive motion that could then be picked up by a sensor, for lack of being able to read their mind, just kind of translate into something like that.
Yeah, certainly you can remove the button interface by looking at the muscle information, but the more aggressive version of what you're talking about is get past the muscles and go back up into the cortex and just measure the response to the brain. So the military has been doing this for a while with Air Force pilots that can willing to train with it for a while, but there's something called the premotor planning phase, which is your brain knows it's going to actually move the hand 200 milliseconds before your hand actually moves. So in very, very high performance systems, you can actually remove 200 milliseconds out from someone's reaction time, and the average reaction time is about 250 milliseconds. So there's some crazy stuff you can do if you're willing to sort of sit down and train with these systems. It's just not very accessible to a wide population who just wants to strap it on and to get work done.
Right, that's why I'm wondering about the cost difference between, maybe you could have some crazy sensors that could, read my brain or read some muscles, but I would think that 5 buttons, or 5 mouse pads, or some 5 very simple sensors could be a very quick way to take in human input like that. Kind of like what you're talking about before, kind of like a cost versus reward type of thing. Mm-hmm, yeah. You know what I mean? So I don't know if everyone's done any research and if you've come across anything like that.
Nothing quite that specific, but yeah.
Gotcha. Okay, thanks.
Just take yours real quick.
Do you know what the current state of the industry is for generating electricity by either walking or tapping into blood or tapping into breathing or?
I don't really, not really. Power generation, I guess parasitic power, human power generation I philosophically actually don't like it very much because that's basically making me work harder. That energy has to come from somewhere, right? There's lots of ways to do it, but I haven't really been keeping track of it. Thanks.
I also have a quick question. Do you know of any do you have any anticipations for neat hobbyist projects when the Wii Motion Plus comes out?
I don't know that much about the Wii Motion Plus, so I can't really comment on it.
Are you looking forward to tinkering around with it and trying it out?
It's kind of low on my priority list because I got a bunch of other things to do. I had a couple requests for doing the rest of my slides. I was just wondering to raise a hand for how many people wanted to actually see those. Okay, do you mind if we switch back to it real quick, just for the hardcore people willing to stick around? Okay, great. Yeah, that was it. That was it. Okay. So where's HCI headed? In my opinion, we're in a local maxima. We're right here with a desktop PC and a laptop PC and awesome keyboards, and these are hyper-optimized environments for the office worker, and that's kind of where computing came from. But there's definitely this range of applications which I think can definitely improve our connectivity and our ability to transmit information into a computer and take information out of a computer. And we're just starting to sort of see movement away from the mouse and keyboard, and mostly these are domains which simply don't support it. So this is the cell phone, this is the living room space, this is in the car, or in these tabletop scenarios where there simply is no space for a mouse and keyboard. And in my opinion, we're not really done until we have the Star Trek holodeck. But if you actually think about this, this is not a computer graphics problem anymore. This is what you can do with real-time computer graphics as of the end of 2007, which is photorealistic as far as most people are concerned. If you look at the latest state-of-the-art in photorealistic computer graphics, this is what you can do. So this is not the problem anymore. These are pretty good images. Most people would hopefully agree. The bottleneck is in the interaction and the input and the immersion. So this is where I think all the interesting stuff is going to happen. And we chased after the holodeck for a long time in research space and military, but what I think is, and by creating cave systems essentially, creating big rooms, lots of projectors, and doing 6-degree freedom input and just throwing lots of VR at it. The problem is that you can't touch any of the objects. Everything has to be 10, 15 feet away and they're all projected. So even though there's in the military scenario, even though there's a Humvee driving at you, you don't feel the Humvee, you certainly aren't going to get hit by the Humvee. What I think is most compelling is sort of these mixed augmented reality in-betweens that sort of carry us forward in these little baby steps where you create displays that look 3D, you create things that feel locally correct, at least with respect to the interface that you generate, or they give the appearance of being mixed in with physical objects, and the physical objects provide you with the tactile experience rather than focus really hard on trying to create realistic macro haptics, which can simulate the feeling of an object. And a lot of the projects you actually saw in this presentation, I think, bring us a few steps forward. That wasn't a very long rant, but that was just my approach to it. If you like this type of stuff, if you like interface technology, these are some conferences I would recommend. This is where Jeff Hahn tends to go to these. Andy Wilson, who's a Microsoft researcher I showed you a lot of work from, goes to these. I attend these. Bill Buxton also, these are the conferences that we like to go to. We find enlightening, interesting, and Paul Dietz also, who's built the Diamond Touch table. The conferences are WIST, SIGGRAPH, SIGCHI, and UbiComp. And that's kind of in my order of preference. But these are just some places where you can find more exposure to this, simply because the popular media doesn't necessarily follow these conferences. Yeah, that's it. So, okay. Yeah. Oh, I can hear you. Just speak up. Just speak up. Okay.
Well, there we go. All right. Basically, fantastic speech, first of all, presentation. Everything that you've presented, though, however, had this common theme of tricking our own sensors to get our mind to experience something. What about shortcutting that entire process and going directly to the electrical stimulus in our mind?
I like that idea. I haven't seen too many successful projects of that.
Really?
The most successful thing I've seen was eye replacements for the blind, and they were able to actually stimulate the eye nerve cortex enough to generate images to the blind person. But they're like 4-pixel images, light, dark. They can maybe pick out a character or two, but doing direct brain stimulation is a little bit sci-fi even for me at the moment. Really? And hard to research because you have to be willing to find human subjects and you have to be willing to implant stuff. But as soon as there's an implant that provides value, sign me up.
Yeah, great. Sign me up too. Thanks.